So this one's a pretty fun one because this is just going to be problem solving. So this is about applications of this flows and cuts. Because for whatever reason, max flow and min cut has like a ton of applications. Um, so I think the way it's set up is I'm going to introduce all the applications and then we're going to go one by one and just knock them out. I don't know if we'll have time to actually address any of them today. So here we'll just introduce the problems and get you excited to come back Friday, where I'll probably spend the whole time reintroducing the same problem and we'll be in an infinite loop. Okay. Um, okay. So I was once inspired to put these in circles. So, okay, there's lots of problems. Um, and so everything here is going to be falling under the category of changing the input. I always claim that we only solve problems in one of two ways. There's a few exceptions, but not many. These are all going to be changing the input. Okay. And yeah, so just not start talking about these problems. So we've already done this one, which is vertex disjoint paths. We did that, I think before spring break. Okay. So that's not so hard. You just have to split them up. In general, you can have vertex capacities on flows and you just split them up, and so that's okay. Vertex capacitive flow is not very complicated. Here's a more interesting one. Bipartite matching. Okay, so this is a bipartite graph. I can split the graph into two parts where all the edges are going between the two sides. Okay. A matching is a set of edges where all the endpoints are different. Okay. So you want to take as many edges as possible so that the edges sort of form an independent set, so to speak. Okay. So yeah, so this has 1, 2, 3, 12 vertices, probably less than 20 edges or so. What is the maximum matching that you can find? You want to take as many edges as possible without any of them touching each other. Five? Anyone else get five? Anyone beat five? I guess the obvious maximum is six because there's only six endpoints on the left, six endpoints on the right. Anyone get six? All right, let's see. I'll point to an edge and you tell me if I should take it. So I'll just go from top down. So this edge, should I take this? Is that a no head shake or a yes head shake? That's a no head shake. Okay. How about this one? Okay. How about this one? Okay. So I guess maybe the idea is here is that, well, this vertex only has one edge incident to it. I should try to use it up. Um, okay. So I can skip some of these because they've already been used. Um, okay, so okay, that means this one's used, this one's used up. So how this one's also used up, that one's used up. Okay, how about this edge? Okay, that uses up this one, that uses up this one. So I think, okay, how about this edge? Yes. Okay, and then how about that uses up this one, that uses up this one. How about this edge? Okay, so there's five edges. Kind of hard to see. Um, and I guess we haven't figured out how to do six yet, right? Okay. Okay, so that's bipartite matching. Okay. So another problem with the same input is called vertex cover on a bipartite graph. This is actually NP-hard in a general graph. I don't know if we've covered that. But you want to take vertices, as few vertices as possible, so that you're taking at least one endpoint of every edge. Okay, so you want to cover all the edges, taking vertices. Now you solve this one as well. So one solution is 6. You can just take one side. So the question then is, can you do better than 6? Oh, we have one better than 6? Okay. There's one of 5. Can anyone do better than 5? So if I told you that this was actually the same graph as the previous one, does that tell you anything about whether 5 is optimal? So it's the same graph as our matching, where we got 5 edges. There's some kind of dual problem, yeah, so just flesh it out. So the usual problem is that, okay, 5 looks good, I can't do better just staring at it, but I really want to know it's the best solution, right? Especially if there's more than 10 vertices or something on the board. It's a big problem, right? Now, you know that there's a matching of size 5, so I will draw one. Uh, I don't know if this is the same one we had before, but there's a matching of size 5, right? Which we felt we couldn't do any better. Okay. So how can I play these problems off of each other? Well, we just want to show like a less than equal to. So if I can show that the size of a matching is always less than equal to the size of any vertex cover, then once I got them to meet, that means I'm done, right? If the max is always less than equal to the min problem, but they meet, then I can't push the min down further and I can't push the max up further. Okay. So here we have a matching of size 5. You're trying to take as many as possible. Vertex cover of size 5. You're trying to take as few as possible. But you know that every edge in your matching, you have to take at least one endpoint, right? And you also know because it's a matching, the endpoints are totally different. So as soon as there's a matching of size 5, you know any vertex cover has to have at least 5 vertices, right? So you have 5 edges in your matching, completely different endpoints. So any vertex cover, just to cover that matching, needs to take at least one vertex from each edge. And they're going to be different. So that tells you that the minimum vertex cover is always at least a maximum matching. So once you got them to match, 5, it meets 5, you know you're done. Okay. All right. So that's another one we'll try to solve on Friday. Okay. Here's a curious one. This is called the project selection problem. So imagine you're a construction company or something, and you're making stuff. You're choosing projects to do. Okay. I think we have at least one project manager here. And so some projects are profitable. They're in green. You do this project, you get 3 chocolates. Okay. But they depend on some costly ones. Okay. So if I take on this 3, I have to also do this project, which is in red and has a negative number. That means you have to pay 8 chocolates. Okay. So your goal is to choose a subset that includes all the dependencies, so you get as many chocolates as possible. That makes sense? Seems practical, right? All right, we'll just stare at this and try to find a solution, and then we all leave. So what's the best you can do? You have to choose, you want to try to choose green, but then the green forces you to choose some red, so there is some trade-offs. Yeah. Yeah, so it has, so if I take 2 and 3, then I have to take -8, -5, but I can leave out 6. Yeah, 2 and -5. So whatever I take everything it reaches. Um, yeah. Okay. So there's one solution. Certainly, like as a local heuristic, that makes sense to me. So this is worth 12 minus 10 is 2. Can anyone do better than 2? All right, so this is tricky. I would say also this one it's not obvious how to certify you have the best solution. There we have some locally optimal, so at least maybe you could present that in a conference room to people with ties or something. But at some level, like whereas vertex cover and matching clearly had these opposite problems with certificates, this one for me it's not clear what an opposite problem would look like. So this is one of the wilder ones. I'll just briefly mention what else we'll do. Playoff elimination. So here you have some teams with a certain number of games left, and you just want to know, I promise you would leave. Another one is assignment. Another one is orienting edges to minimize the maximum degree. And the last one is trying to find the densest subgraph in a graph. Okay, so I'll reintroduce them last time, but that's all of them. And we'll end there. All right, thank you. That's fine. Okay, so we're going to continue this applications of flows and cuts lecture. This is really probably one of the funner lectures of the year because we're just going to knock off problems. We've already have some tools in the bag that we just have to apply now, and the applications are kind of neat. So we reviewed several of them. A few I didn't quite get to, so I'll finish off touching on all the problems that we'll do today, and then we'll actually do them. So this is just to remind you, you already know how to do vertex disjoint paths. We talked about bipartite matching. You're trying to take a lot of edges. Bipartite vertex cover. You're trying to take a small number of vertices so that you're touching every edge. I think this is the last one we probably discussed in detail. That's this project selection problem. So here you have some net profits, some negative cost things, and or negative profit, positive cost. And so you're trying to choose something that maximizes your profit, but you have to take all dependencies. We'll do that. Okay. So another cool one is playoff elimination. So like we have at least one Red Sox fan here, I think. And so this isn't very realistic because If you actually wanted to know if Boston can catch the Yankees these days, the answer is just no. It's been that way for a couple years. But in years past, it might have been more competitive, right? So your favorite team is the Red Sox. Um, and your least favorite team is the Yankees. And you want to know if they can make the playoffs. Okay, so all you know first is that, okay, this is how many wins each team has. And let's say, or at least tie for first. Okay, and then you have some arbitrary playoff play in. And you know that this is how many games left for each team, right? And then you look at this and you say, well, okay, if the Red Sox win all their games and everyone else loses, then you should be able to get 92 and catch up to the Yankees, right? But it may not be that simple because these teams might play against each other, in which case somebody has to win. So your full data might look something more like this. So New York is going to play Baltimore and Toronto one time each. Baltimore is playing New York and Toronto and Boston. Boston is playing Baltimore and Toronto. And now you have this chart and you want to know, can the Red Sox, the Boston Red Sox, still make it to the playoffs? Does the question make sense? All right, so I'll let you look. Tell me if it's possible. There's no ties in baseball. Oh, but you just want to tie for first to kind of make the playoffs. Then they'll have a separate tiebreaker game. Yeah, but yeah, it's not possible. Why? Okay, so even if you gave Boston both of the wins, you know the Yankees have to lose both of their games. So we'll assign these two Yankee games to the other team because if the Yankees get 93, then you're out. And now the only unallocated problem game is this one game between Baltimore and Toronto. Somebody's going to win. Someone's going to end up with 93 wins. So no matter what, the Red Sox are eliminated. Okay, so we'll figure out how to do this automatically. Okay, here's another one. This problem actually motivated a lot of research into this problem because I think during things like World War II, they're allocating a lot of people to bleak outcomes. But they're organizing a lot of things, a lot of central planning, and they want to do it optimally in some sense. So this is called an assignment problem. You have let's say m individuals and n jobs, and you want to fill as many jobs as possible. Okay. And the only catch is that not everyone is qualified for all the jobs. So probably back then they would express this in a matrix where one means this blue person is qualified for this red square, and one means this blue person is qualified for this red square, uh, and so forth. Okay. Um, there's also generalizations of this problem where each job can take more than one person. You need 5 people to do this, 8 people to do that, and so forth. Okay? But it's an assignment problem and you have some kind of restrictions. So I guess if this was your input, is it possible to assign to fill up all the jobs? Yeah, I guess not. 'Cause it looks like there's these two jobs here and there's only one person qualified for them. So you can get 3, it seems like. All right, so that's another one we'll do. Okay, here's another problem. So I give you an undirected graph, and your goal is to assign directions to all the edges. So you minimize the maximum in degree. So it's a load balancing problem. So something like, oh, you can try to direct it, these 3 edges this way, maybe that edge is directed that way or something. You get to choose. And your goal is to minimize the maximum in degree. I guess I can ask you to try. I feel like this is very hard to do in your head. Uh, so I guess 5 is always possible because the maximum undirected degree is 5. The question is, can you do 4? Can you even do 3? I feel like it's a little hard to stare and figure this out. Uh, Here's some solution. I don't know if it's the best solution. But the maximum in degree here is, I guess, 3. So 3 seems to be possible. I don't know if it's possible to do 2, but there is one that does 3. Okay? That's sometimes called the arboricity problem. Here's another problem that comes up a lot for people analyzing real networks. It's called the densest subgraph problem. So in general, if you look at a graph, they sometimes say the density is m, the number of edges, divided by n, the number of vertices. So if it's a simple graph, so you don't have any kind of parallel edges, n is the maximum density because that's n squared divided by n. You can have at most n squared edges. Yeah, but if it's weighted, it can be more interesting. So we can also talk about subgraphs, where I look at this subgraph of these 3 vertices, okay, and I'm only counting the edges inside the subgraph. So edges on the periphery don't count. So this would have density 1 because there's 3 edges and 3 vertices. Okay, so the question is, what is the densest subgraph? Yeah. No. Could be. So it's not necessarily the whole graph because you want to maximize density. So okay, so for example, people have a social network and they want to identify communities. And the idea is that okay, if everyone's going to the same school, you're going to see a lot of edges just between the people in that school, right? Or you're looking at some kind of weird biological data and you somehow you detect cancer. I'm not really sure, but I read it somewhere. Um, I think if you're a security agency and you're monitoring like phone networks and you find like abnormal communication patterns between a group of people, right? So you're looking at more than just like one particularly heavy edge. It's like, okay, here's a conspicuous group. So sometimes those are small, sometimes those are big. And this is agnostic. I mean, um, uh, yeah, yeah. So you just choose a set of vertices and you count the number of edges within that set. Okay, so all right, so for this graph, what's the best you can do? Okay, so there is a click planted in the middle. So these 5 vertices have how many edges? 10? 9? 9 to okay, we can do better than 9 to 10. Exactly how many edges are in this subgraph? 10, okay. I'm trusting you. And so the density would be 2. I'm not 100% sure if this is the densest in the subgraph, but it might be, right? So, for example, I don't know if this has come up in our homework or not. Finding the largest click in a graph is MP hard, and it's really, really hard. Uh, it's actually the opposite. You can start with independent set, right? That means there's no edges between the vertices, and you look at the complement graph. So you make a graph where every time there's an edge, you get rid of it, and every time there wasn't an edge, now you add an edge. So an independent set in the original graph will correspond to a click in your opposite graph on opposite day. Okay. So it's really just independent set. So also looking for a click is something people often want, also for community detection and things like that. They look for large clicks. Trying to find a large click is really, really hard to do. It's also very hard to approximate. We won't talk about too much, but you can't get within like you can't get an n to the 0.99999 approximation. In other words, you get some click, and you can't get anything better than like strongly better than a factor of n closer. And a factor of n is like very easy because there's n vertices, right? So both independent set and click are also very hard to approximate. So people often use it dense subgraph as some kind of like, it's similar. And we'll see in this class we can do it. Okay. Okay. I think that's all the problems I had prepared. But if you want more, then you have a lot of great homework to look forward to. I mean, there's lots of fun problems. So, yeah. Okay, so let's start solving these. So we learned how to do max flow, been cut over the past few days, as well as disjoint paths. I want to add one more piece of information that I didn't really highlight in the lecture on Monday and Wednesday, which is if your capacities are integer, even with flow where you're allowed to take any value, if your capacities are integer, the algorithm outputs an integral max flow, right? Because it's always just routing as much of flow as possible, and that'll always be an integer, right? Which will be sometimes interesting for some of these applications. Okay, because sometimes it's hard to interpret a fractional flow, but you can interpret in terms of whatever combinatorial story we started with an integer flow. That's one more thing. It's also interesting that there always exists an optimal integer flow. Okay, so having established that, so in bipartite matching, I'm giving you this bipartite graph, and you want to find the maximum number of edges so that they don't touch each other at all. And everything in this class, we're going to try to use flow to solve it, or more or less equivalently disjoint paths. How do you do it? Okay, where would I add a source and a sink? Oh, you know you need to add a source and a sink. Yes. Yeah. Both? Okay, we'll put them on opposite sides, like this. So you want to kind of, so if we're trying to use flow, then sort of a path or, a unit of flow should correspond to like a decision, something we take. And so you can sort of see that's how we're setting things up here. Okay, like this. And then we'll add capacity 1. How should I interpret the capacity 1? Well, what was our main constraint for this problem? A distinct endpoint. So at some level, if you're trying to send flow from S to T, which you're hoping uses a middle edge, and that'll correspond to an edge you're taking in your matching, you know that each left vertex is only allowed to be incident to one edge. So you should only be able to send one unit of flow through that vertex, and that's encoded by this source edge having capacity 1. Okay. Um, there's at least one more thing to fill in, or we're not done yet in this picture as written. Yeah. Yeah, so there should be a directed graph, unless you really mean to add both directions. So I'll direct everything from left to right, which is probably what you had in mind. Okay. And one more piece of information. Yeah, you need some capacity. So the full input of the problem needs to have capacities for all the edges, directions for all the edges, and a just clear source and sink. Okay. So that's a construction, right? So okay. So this is the one I did ahead of time. Oh, I put one in the middle, but that could also be infinity, and that'll be okay. So what's the idea, right? You want to argue that you have some correspondence between matchings of, say, size k and edge disjoint path or flow of size k from S to T, especially integral flows. Okay, so uh, so I'm guessing right. So at some level, like taking this edge here, right? You would interpret that, or that would map to a flow using that edge, right? Or a path using that edge. So you can look at this graph and say, okay, all the paths from S to T have this very simple form. The only way to go from S to T in this graph is one of these edges. Should be directed from left to right. And then one of these edges and one of those edges, right? There's no way other way. And so all the paths have this form. And now you just need to show that, okay, for any matching of size k, I can get k of these paths and vice versa. And the clear thing is, okay, if I have the mapping is going to be, okay, I'm going to identify each of these paths from S to T with the middle edge. That tells me everything, right? So if I have a matching, I want to check on feasible for the flow. And the main constraints we need to worry about is the source and sink constraint of one each. But if it's a matching, there's only one edge incidence to each vertex, so you should only have one unit of flow. So you start with a matching and check that it's a feasible flow or a feasible solution to the flow problem. Okay, and you just check, oh, you satisfy these capacities, oh, these are all paths. It should be, by the time you got to this point, it's probably somewhat straightforward. And then vice versa, every time you have, k paths from S to T and they satisfy these capacity constraints, I can extract a matching. And now I just need to double check that I'm only using each endpoint once. And you say, okay, well, I can't use this vertex twice because there's only capacity one here. Okay, so you just have to double check both directions. So by the time you've kind of drawn the right picture for yourself, hopefully it's relatively straightforward. It's more of a verification when you do the proof. Okay. And you only have to write like uh, a sparse, slightly confusing version, and ChatGPT will fix it from there. Okay. Just kidding. Kind of kidding. Okay. Um, okay. So that's bipartite matching. That's a good one. This one's a little trickier. It's bipartite vertex cover. Okay. So matching was nice because, okay, max flow, max edges, that would be easier to see. But now you're doing a minimization problem. I'm trying to take the minimum number of edges so that I'm incident. I take at least the minimum number of vertices, so I'm taking at least one vertex incident to each edge. This is less direct. Any ideas? Yeah. So here's our construction from before. So you run st flow. Yeah, you get some edges. Okay, so if I fix some solution here, um, I don't know if this will be maximum. So you can run max flow on this graph we had before. Um, okay. Now you do need to, our goal is to output vertices. That's one thing to keep in mind, right? And we just did this nice correspondence from edges to paths. So how would you choose which vertex? Yeah, sure. But what if I actually asked for the vertices? Okay, so this example is a little silly because the answer is 6, so you can just take both sides. Let me make it a little bit more interesting. Um, by removing that edge and maybe removing that edge. So now I think the answer should be 5. I don't think you can do better than 5. And to prove it to you, here would be a vertex cover. Oh, let me also erase this edge then. Okay, so I cheat a little bit. But here would be a solution at least where the vertex cover is not just one side. Okay, and so uh, and here would be a solution for max flow or something. Yeah. What if okay, so it looks like these have higher degrees than these, and same with this side. Okay. Well, okay. First, it's a little bit of a small example, but two, I think I can always hack this by adding a bunch of edges. Oh no. Uh, well, okay. The answer is that doesn't quite work, but it's a little hard for me to draw a counterexample given what we have. Uh, well, okay. Um, oh, okay. So maybe there's two hints towards what the eventual solution is. One is that we're minimizing instead of maximizing. So max flow at least will always be a little off from minimum vertex cover, but minimum is in front of the word st cut. And in this particular example, we talked a little bit, I think, about how matchings and vertex covers are actually dual to each other. So if matching is like flow, then you might hope that the dual of matching vertex cover is like the dual of flow, which is st cut. Okay. So um yeah. Now any st cut. So the way I've drawn this graph, this time I made sure the middle edges have infinite capacity. Okay. So, for example, consider this partition of the vertices. So everything on the left is the S side of the cut. Everything on the right is the T side of the cut. Actually, let me draw that differently. You wouldn't want to do that. It would look like this. Okay. In particular, because all the blue edges are positive infinity, right? I don't want any blue edges going from the S side of the cut to the T side, because that'll be a huge cut, right? And you look carefully here, every time blue goes across purple, it's actually going from the T side, the sink side, to the source. So every ST cut is basically going to take your two sets of vertices, your left and the right, and put some of them on the source side, some of them on the sink, some on the source side, some on the sink. Okay? And the size of the cut, if we look here, I'm cutting two of these source edges and three of these sink edges, and you're getting 5. Okay? So for every vertex cover, I can take this, I can kind of reverse engineer this. So I can take the source, the left side vertices of the vertex cover and put them on the other side of the cut. I'll cut those two. And then same with the sinks, the ones in the vertex cover, I'll separate. Okay. And it'll guarantee that for every, um, yeah. So for every edge in our original matching, since I don't want it to be part of the cut, okay, then the one thing we'll never have is we'll never have the blue side on the source side. I mean the left side on the source side and the right side on the sink side, because that would be a cross your cut. Okay. So okay, just to be clear, what the algorithm what we're going to do, we're just going to compute the minimum ST cut, which comes for free with the maximum ST flow. And I'm going to read off which are the left vertices on the sink side and what are the right vertices on the source side. Okay, source here is same side of the purple line as the source. Okay, yeah. So the edges that are actually cut are just these 3 sink edges, which is saying, okay, those 3 vertices are going to be in my vertex cover. And also these 2 source vertices, or left side vertices, sorry. And it's the 2 source edges that are cut. So every cut sort of source sink edge is going to correspond to a vertex in my vertex cover. So we just have to go back and forth in both directions, right? So given an ST cut, you know, I want to make sure that I'm covering all of the edges. Okay? So like an edge, each edge here, each edge in your matching represents a path from S to T, right? So in order to cut that path, and since the middle edge itself is infinity, you have to cut either the starting edge or the ending edge to make sure there's no ST paths. Right? So an ST cut will guarantee there's no way to go from source to sink. So for every one of your middle edges, which gives you a potential source or sink path, you have to cut one of these 2 endpoints. Okay? And it's the edges that you cut are the edges correspond to the vertices that you're taking. So if we did it more slowly, say, okay, let's say I have a vertex cover. I'm going to make a cut where I cut the edges of all of the corresponding vertices in my cover. Okay, and I need to argue that gives you an ST cut. Okay, I'm going to remove those edges. Say, oh, for any path, that path I identify was a middle edge. And that edge, one of the endpoints is in the vertex cover, and that endpoint's either source edge or sink edge had been cut, so that's no longer a path from S to T. Okay, so you check them all off. There's no ST path left. You have an ST cut. Okay, and then vice versa, if you have an ST cut and you map that to a vertex cover by saying, oh, if I take the source edge, I'll add that. If I take the sink edge, I'll add that. Now you want to know it's a vertex cover. I say, well, give me any edge with two endpoints. I know that represented an ST flow. And so at least one of these two edges have to be cut, and the corresponding vertex is my solution. So we have a vertex cover. Yeah. Yeah, so the edges going across purple, those are the ones I'm deleting in the cut. Yeah, so the original problem is I want to take vertices to cover all the edges. One, two, three. This one? Oh, we're not discarding it. We're going to discard this one. So you're going to take as few vertices as possible so that you cover all of the edges. The fourth one is covered by taking that endpoint. Yeah, you just need just one of the two endpoints. Otherwise, you have to take everything, right? It's not super interesting. So, yeah, yeah. So SD cut is always a little bit trickier. So it's probably usually a little less direct compared to flow, but we'll get some practice and then we'll get better at this. Okay. Any questions? Okay. Oh, here's the coolest one, in my opinion. Um, project selection, right? So remember this problem? I'm trying to take as many as possible. This is the trickiest, but maybe it's still fun to give it a try. So try to figure out how to use max flow min cut. Yeah. Okay, so I need sources and sinks. So where should I put my source? The sink's on the right, okay? Okay. So if you take 6, then you have to take -3, and you have to take 2, and then you have to take -5. Oh, you're partway there. I mean, we haven't finished also the sink edges yet. Okay. Now, we don't really have a notion of negative capacities. It's not clear what we should make those edges worth. Two sources. Sure. A second source here. So this is like going this way now. And into T. Well, if I'm just going to draw from red, why didn't I just leave T where it was? Literally put on the other side. So, okay. Okay, doesn't think it matters. Sort of pessimistic, but sure. Well, right now we just chose the green number for the source edge because yeah, I mean I think the numbers are going to matter, right? Like the numbers need to enter your algorithm because otherwise you won't be able to distinguish solutions. You just have to figure out how. Okay. Suppose I told you that what we are going to do, this still doesn't explain everything, is we are going to just add this with the positive version of the number. Okay, so sinks will go into cost will go into sinks with the cost labeled on the edge. And the other thing we're going to do, so we were on the right path, but instead of making these worth one, because the dependencies are sort of inviolable, I'm going to make this positive infinity. That's going to be our float network, but I still haven't explained how we actually get a solution. So now I'll try to let you think about that. So what's the intuition behind that? Um, so yeah, but you're getting close. Does anyone? Yeah, actually, what if I told you where it's actually not going to be based on max float directly? Instead, we're actually going to be looking at the minimum ST cut. So I think the solution we had suggested before looks something like this. If I remember correctly, your answer was to take the top three green ones. Okay. So, okay, if you look at any ST cut, and you say, okay, I'll just take everything on the S side, let's just first double check the dependencies. It has to contain all the dependencies, right? And the dependencies have positive infinity. So once I take this green project, I know I have to keep it on my S side of the cut, right? So it's going to be on the same side. And I'll make sure that I don't have any purple edges going from the source side to the sink. The other direction is fine. They don't hurt us at all. Okay. Now, how can I try to interpret this? So usually like cutting an edge, that's something kind of bad, right? So for the cost, it kind of makes sense. Okay, I cut this, I add this cost, I pay 5. I add this cost, I pay 3. I add that cost, I pay 2. So that's kind of directly reflected in the cost function, right? But now how do I interpret like a green project being given up? Yeah, like it's like giving up 3 possible points. So I want to minimize the lost opportunities, the lost profits, as well as the costs being incurred. And that would be the same as maximizing the total profit. Because there's only a total amount of profit here. So if you tell me how much profit you gave up, I can tell you how much profit you got. So that's the idea. Actually, I think it's going to coincide with your suggestion. So if I compute the minimum ST cut, which will give me a sum that includes the profits I gave up plus the costs I'm incurring. Now to get the actual profit of my solution, I just add up all the green and then subtract that number we just got. So subtract out this 3 and it'll subtract out the costs. Okay, and then vice versa. You're giving any particular selection that also contains all the dependencies. Now we just have to extract the cut. We know that we're always going to kind of contain or not violate the purple edges because they're positive infinity. And then we just double check in the opposite direction. Is that okay? I can do the arithmetic down on paper, but it'll just be exactly as I said. So yeah. Um. So why didn't I draw the purple around here, around 3? Oh, are you worried about? Oh, why did I? Do I want to? Do you want me to change this cut and take a look? Yeah. Yeah. Okay, so this edge, see, are you worried about this edge here? Because it looks like there's a big edge going through the dark line. So one thing to keep in mind is that when we're looking at a directed cut, so I'm only looking at edges going from the source side to the sink. So this edge here, which seems to be bad because it's going across the dark purple, 3 is actually on the sink side of the cut. So it's going the opposite direction. It's going from the sink to the source side, so it doesn't count in the weight of our cut. So for us, the source is above this dark purple line. So I'm only counting the edges going from the source side of the dark line to the sink side of the dark line. So if we compute the minimum ST cut and interpret, oh, whatever's on the S side is the projects I take, then just to make sure that I don't have any positive infinity going from source to sink, because that would be bad from a minimum ST cut point of view, I would always have to include all of the downstream projects I depend on the source side. Because I don't want to like take 2 and then leave out -5. If I had left out -5, then my minimum that the cut size would become infinity, and that can't possibly be the minimum. Yeah, I'm not sure if I answered the question though. Okay. Okay. All right, we only have a few minutes. We can at least do baseball. And whatever I leave out, you can check the notes. Okay. All right, so baseball is kind of fun. So again, the input is really a table like this, and you want to figure out if there's some set of outcomes to guarantee, in this case, that the Red Sox can make the playoffs. How can I turn this into either a flow or a cut problem? All right, as a hint, given the time constraints, suppose that I told you we're going to use flow. And flow, often each unit of flow is allocating something, but what would you be allocating? A win. So we can try to set up a graph like this. So these are all the games we have. There's one game between New York and Baltimore, New York, and each of these have to go to somebody, right? So well, I'll just show the picture. Okay. So these should be unit capacity edges. Okay. So New York versus Baltimore, one unit of flow needs to go to somebody towards the end. Okay. So I have these games and they're directed to the teams that are participating in the game. And I have the source edges are one because there's only one win to hand out for each one. Okay. And now one key thing is the right hand edges. So if I look at this table, I know that I can only afford to let Baltimore win one game and Toronto to win one game while the Red Sox can still make the playoffs. And I can't let the Yankees win any games, right? So what this is saying is, what I'm saying, can I send really 5 units of flow from left to right in subject to these constraints? It's saying, can I assign wins to each of these games so that New York wins at most 0 times, Baltimore wins at most 1 time, Toronto wins at most 1 time, and Boston can win as much as possible. That's fine. Okay. And so you'll compute this flow and you'll get that the answer is 4 because it's not possible. So we'll get a minimum cut that's less than all of these, right? And that will tell us, oh, it wasn't possible to assign wins to all the teams in a manner that lets the Red Sox tie for first. Okay, and then with more time, you do it a little bit more slowly and go back and forth, but that's the idea. So we're trying to allocate wins, but we have some constraints here. Can you allocate in a way that doesn't use too much of this, too much of that? And then so you'll compare this problem compared to others. You'll look at the answer from your flow and compare it to the number 5. Was I able to allocate all 5 games? If the answer is no, then it's impossible. If the answer is yes, then the pass will tell you some set of outcomes that makes it possible. Okay. Yeah. Okay. So I know that Boston has at most 2 games left, and in this case, yeah. So if I gave you a more interesting or bigger table, well, you can just say who's in. You can figure out what's the maximum Boston can win, right? Because I can just add up. Oh, let's say Boston wins all of its games. Best they can do is 92, and then I compare 92 with how many they've already won. The Yankees already won 92, so they can't win anymore. Baltimore has already won 91. They can only win one more. Yeah, I should have said that. So that one will also require a little bit of pre-processing, but it's not too bad. Yeah. Okay, so that's the baseball one. So the other ones I didn't mention, one is assignment. That's not so bad. That's like bipartite matching. Uh, Edge orientation turns out to be bipartite matching in disguise because you're trying to assign edges to one of the 2 endpoints that is directed towards, right? And you're trying to minimize the maximum in degree. And then it turns out the dual will give you denser subgraphs, so you end up doing a different, same construction. Okay, we're out of time, but you can read about it in the notes. Okay, we're done. Thank you. I guess Monday I'll just print out some problems and we'll just chit chat. Yeah, so be prepared to make friends and all that.